Hey, welcome to another session on maths for data sciences. So we have already looked at a variety of discrete distributions in our previous sessions. We looked at uniform discrete distribution, we looked at binomial distribution, we looked at Bernoulli, geometric and Poisson distribution. We also looked at how we can compute the expected value, that was the mean, and the variance for each of these distributions. And in fact, we were able to derive these values for each one of them using the expected value definition, where the expected value was calculated as the sum product of the values of that variable with their corresponding probabilities. And variance was computed as the difference between the second movement of the random variable, that is expected value of x square minus the square of mean. Now once we did that, we were able to get certain properties, mean and variance, and here in this particular session we'll be looking at a couple of more discrete distributions, for which we will not be looking at the deriving the mean and variance, because it could be a very long process to derive. They are a little complex discrete distributions, and therefore we'll not be looking at the mean and variance, but we'll be looking at how these distributions are defined and what is their probability mass function and how we can get that particular probability mass function in general. So the first one, which is our sixth discrete distribution now, we'll be looking at is something called a hypergeometric distribution. Now we'll try to differentiate this hypergeometric distribution from binomial distribution. So we'll see how it is different from a binomial distribution, because there are certain similarities between the two of them. Now in binomial distribution, we had a couple of parameters. One was the sample size n, or the number of trials, and then we had a p, which is the probability of a successful trial. Now if you remember, we also had looked at 4 assumptions of a binomial distribution. So we'll just revise them quickly here. The 4 assumptions were: the sample size should be fixed, so the value of n should be a constant here. Then all trials should be independent. So basically what this means is the outcome of one trial, whether it is successful or not, should be independent of outcome of any other trial. Third is each trial had only 2 possible outcomes. So either the trial could be a success or it could be a non-successful trial. And then P is same for each trial, which means the probability of success for each of the trial is independent, and it is also equal for each trial, and it is equal to P. Now the difference comes for hypergeometric distribution is, in case of hypergeometric distribution, we already let's say we have a box, and we have, let's say, certain purple balls here. So let's say we have 10 purple balls, and let us say we have 5 blue balls here. Now just like we had 2 parameters n and p for binomial distribution, we have certain parameters here as well. There are a slightly more number of parameters here, so we'll define those parameters here. N, capital N, denotes the population size, which is in this case 15, since the total number of balls in the box here is 15, so n is nothing but total number of balls in this case. Now next parameter we have is capital K, which is total number of success in population. Now success here could be defined by either a blue or a purple ball. Let's say in our case the success is defined as a blue ball. So the value of K in this case would be 5, since there are 5 blue balls out of the total 15 balls here. Now the probability, so now there's another parameter which is called small n, which is the sample size collected from the box. Now the probability mass function, or let's say the probability itself, so we define this distribution. Let's say we have a random variable x. Now this is a random variable which has a hypergeometric distribution. Now what we mean by hypergeometric distribution is, it is the number of successful trials in the sample collected. Now we are taking out a sample of n, small n here. This is the sample size, small n, and we are taking it out from a capital N population size in this case. So first what we look at is, now let's say we have to calculate the probability mass function for this particular random variable x, and this is calculated as total number of ways to get small x blue balls from k blue balls. Now in the sample, if we want small x successes, which means small x blue balls, we are essentially pulling out small x blue balls from a total of k blue balls, which is 5 in this case. So we are pulling x blue balls from 5 blue balls, and then we still have to push another, pull another. So we'll multiply this. So instead of this, let us say we use a star for multiplication. Total number of ways to get small n minus x, because we have already pulled x blue balls, we still need small n minus x purple ball from n minus capital K purple balls. Now in this case, since we had capital K blue balls, obviously the total number of balls in the population was capital N. So the total number of purple balls would be capital N minus capital K, and we are pulling out small n minus x purple balls from these n minus k total purple balls. Now in the denominator, so this is the numerator with two terms here, and in the denominator we will have total number of ways to collect n out of n balls. So now let's look at it once again more granularly. So let us say we are pulling out small n number of balls from a total of capital N balls. So we are pulling out a sample size of 5, sample size of small n. So let us say we are, in this case, we can assume a particular value of this small n. Let us say we take it as 6. So we are pulling out 6 balls from the population of 15 balls, and we want that out of those 6 balls which are taken out, there should be small x number of blue balls. So for that, we need to pull small x number of blue balls from total 5 blue balls, and which is once again, let us say we also, let us say, assume the value of small x here. So let us say we are calculating px equal to 2 here. Now we are collecting 2 blue balls from 5 blue balls. Now let us go back to our session on permutations and combinations, where we looked at how a combination operator is defined. A combination operator was defined as the total number of ways to select x item from n items, and we defined it as ncx. So this was total ways to select x out of n items. Now in this case we are using combination and not permutation, because the order of selection is not really important here. We only need to select x from n balls in this case. Now the first term here is we are selecting 2 out of 5 blue balls. So this will become 5C2, and then there are 10 purple balls, and we have to select the remaining 6 minus 2 balls, which is 4 balls from these 10 purple balls. While the total number of ways to select 6 balls from total 15 balls is given as 15C6. So this is how we calculate the probability for this particular distribution or this kind of a random variable. Now this can be written in a more generalized way as P x equal to x, and we are selecting, so we are selecting NCX, so small n, KCX, because there were k number of blue balls, so we are selecting x blue balls from k blue balls, and then we are selecting from n minus k purple balls, we are selecting small n minus x purple balls, which is, and then in the denominator we are simply selecting small n balls from capital N, therefore it becomes NCN in this case. Now in this case we can also write the combination operator in this particular way. So this is another way to write the combination operator. So we can write it as this is the required probability mass function for a hypergeometric distribution, and using this particular example which we saw here, we can actually also calculate these probabilities. Now if you remember, NCX, a combination operator, is computed as n factorial divided by n x factorial n minus x factorial. So this can be now calculated here as 5 factorial upon 2 factorial, and 5 minus 2 is 3 factorial multiplied by 10 factorial divided by 4 factorial, and 10 minus 4 is 6 factorial. This whole divided by 15 factorial divided by 6 factorial multiplied by 9 factorial. So this is how we can calculate the probabilities in a hypergeometric distribution. Now the major difference from binomial distribution here is, in this case there are 6 trials here, that is the small n. So we had small n even in binomial distribution, we have small n here as well, and both means the same, like we are taking out a sample of 6 balls in this case, and similarly in binomial distribution also we could have a sample of 6 balls. But the point to note here is, in case of binomial distribution, the probability of getting the blue ball would remain the same for each of those 6 trials, but in case of hypergeometric distribution that is not the case. So we'll see that why that is not the case. So let us say we select our first sample here, n equal to 1, and the probability of getting a blue ball is what? In the first sample the probability of getting a blue ball is 5 by 15, since initially we have 5 blue balls in total, 15 total balls, therefore it is 1 by 3. Now for n equal to 2, that is the second sample, in this case we are only left with 4 blue balls out of total 14 balls left, and therefore the probability becomes 2 by 7. So the catch here is, since the number of blue balls in this case is fixed, as and when we draw a blue ball from the bigger box, the probability of getting the blue balls in the next trial would be different from what it was in the previous trial. So another major difference is, what happens in the previous trial will determine the probability of getting a blue ball in the next trial. So just to show that concept, let's say for the first sample we are selecting a purple ball in the first sample. So we have 10 by 15, as there are 10 purple ball initially, this becomes 2 by 3. Now for n equal to 2, we are getting a blue ball now. So this will become P, we still have 5 blue balls, but we have 14 total balls in this case. Now if you look carefully, in this case the probability is 5 by 14, but in our previous case the probability of getting the same blue ball was 2 by 7 in our second trial. Why that is happening? Because in this case the first ball which is drawn in here is a purple ball, while in our previous example which we looked at, the first ball which was taken was a blue ball itself. So the probability of getting a blue ball in the second trial here is actually dependent on what happened in the first trial, and therefore the events here are not independent of each other. So just to reiterate here, the different properties, let's say once again, if we look at properties for a hypergeometric distribution, the trials are dependent here, they are not independent, unlike binomial distribution where the probability was same for each of the n trials and we were using the same probability parameter. But in this case, the probability will change depending on what happened in the previous events, and therefore the trials are dependent on each other. And P is obviously not equal for each trial. As we saw in our previous first example here, the probability was 1/3 and then it changed to 2/7 in the second trial for getting the same blue ball. Yeah, so these are the two major differences between the binomial distribution and hypergeometric distribution. For hypergeometric distribution, one has to remember that the total population size, total number of successes in that population, and the total sample size are fixed, and therefore the probability of getting a success in a particular trial is actually dependent for that trial with other trials, what happened in other trials as well, as we saw in these examples here. So this is it from hypergeometric distribution. We'll be looking at now another distribution. So this will be I promise last discrete distribution, and we'll actually be covering it in a little brief manner. So it's called a multinomial distribution. Once again, we'll be trying to differentiate this with the binomial distribution itself, because again there are some similarities in this particular case. Now what happens in a multinomial distribution, we have certain parameters. So let us say we have a sample size in n, but instead of having a one probability value like we had in binomial distribution, we can have multiple probability values here. So let us say we have two probability values here, p1 and p2. Now what this shows here is, let us say we roll a die. Now in case of rolling a die, there could be multiple outcomes. We can have a 1, we can have a 2, 3, 4, 5 or a 6. The probability of getting each of these outcomes for a fair die would be 1/6. Fair dice would be 1/6, and therefore let us say now one has to define a random variable with a multinomial distribution. Let us say in the random variable x, we are trying to model the number of 6s, 4s and neither. So there are three possible outcomes for each of the trials in this case. Let's say we are rolling. So let us say we are rolling the dice 10 times. The question is, calculate probability of getting 5 6s, 2 4s and 3 other outcomes. Now how we can solve this particular problem with multinomial distribution is, first we need to get the required parameters. So we can define the random variable here, and it could be defined as multinomial. The sample size is 10. The probability of getting a 6 on any of the trial is 1/6. The probability of getting a 4 in any of the trial is 1/6 again, sorry. Also there is another outcome which is other outcome, and the probability of that would be 4/6, because obviously since we are only looking at 4 outcomes there, the remaining ones, which are 1, 2, 3 and 5, the probability of getting one of these 4 would be 4 by 6, and therefore the probability of getting this third outcome could be 4 by 6 for each of the n equal to 10 trials. Now to calculate the probability here, what we can do is, again, we'll try to calculate it in word form first, so that things become clear how the probability mass function could be derived at. So the probability of getting 5 6s, 2 4s and 3 others would be what? Total ways to select 5 of the 10 trials which will get a 6 as an outcome. Then we multiply this by probability of getting a 6 5 times in those 5 outcomes which we have already selected. This is multiplied by total ways of getting 3 of the, we need 2 4s, so this will become 2 of the remaining 5 outcomes that will get a 4, multiplied by probability of getting a 4 twice, and then probability of getting other thrice. So for the last case, where we are trying to get one of the 4 remaining digits, 1 2 3 or 5 in 3 times, since we are only left with 3 trials, we don't need to select, because selecting 3 out of the remaining 3 would be, there's only one way to do that. So we straight away are using the probability in that case. Now once again, using our combination operators, we get the required probability as 10C5. Now what 10C5 does is, it selects 5 of those 10 trials which will get you a 6. We multiply this by 1 by 6 raised to power 5, since we are getting the digit 6 5 times, and the probability of getting the digit 6 is 1 by 6 for each of the trial. Therefore we are multiplying 1 by 6 5 times. Then we need to select 2 of the remaining 5 outcomes that will give you, that gets a 4, and once again the probability of getting a 4 is 1 by 6. Therefore we raise it to pass 2, and then probability of getting others was 4 by 6, and we are getting it thrice. So this is how we can calculate the probabilities for multinomial distribution. Now the difference, as you would have already observed from binomial distribution, is in binomial distribution there were only two possible outcomes for each trial, and the probabilities of those outcomes were P and 1 minus P. So if you remember, like, you might want to go back to binomial distribution, how we came up with the binomial distribution probability mass function. What we were doing was, we were selecting x out of n total trials, and then probability of getting a successful trial x number of times, therefore p raised to power x multiplied by 1 minus p raised to power n minus x, because if there are x number of successes, there will be n minus x number of failures, and the probability of failure for each trial is 1 minus p. Therefore it is raised to power n minus x to get the probability mass function in this case. And in multinomial, we have actually used exactly same principle to come up with the probability mass function, but instead of having 2 outcomes, we can have multiple outcomes here, and therefore we'll have to make these multiple selections using 10C5 here and 5C2. So 10C5 is the number of ways to select 5 out of those 10 trials where we'll get a 6, and then out of the remaining 5 trials we are selecting 2 trials where we'll get a 4, and out of the remaining 3 trials we are selecting all those 3 trials where we'll get a others. So if you even put 3C3 here, this is nothing but equal to 1. Therefore we simply ignored it in this particular case, since we are anyways multiplying these terms. So this is regarding multinomial distribution, and the major difference here was from binomial distribution is there are multiple outcomes possible for each trial for a multinomial distribution. So this is it from discrete distributions. We have now looked at 7 discrete distributions. These are the most common ones which could be encountered in certain problems, and yeah, so from next session we would be introducing continuous distributions.